Okay. Where we were last time is we were talking about current, and in particular, we were talking about streaming current, the current that's induced by fluid flow. And we went through and we determined that the electrokinetic coupling coefficient associated with streaming current was in fact similar to, or was in fact equal to, that electrokinetic coupling coefficient that we find for electroosmosis. So just as we could say that the average velocity, or volumetric flux normalized by cross-sectional area, that we induced by an electric field, just as the proportionality constant for this was given by minus epsilon times phi naught over eta, we also could say that when we go to measure the net current density that's generated by a gradient in pressure, the proportionality constant here is also given by epsilon phi naught over eta. And I waxed philosophical a bit at the end of last lecture about how this highlights the fact that despite the fact that the thing that's carrying the current is always charge density at the wall, volumetric net charge density in the fluid, and despite the fact that its distribution and its magnitude is a function of lambda d and the details of the electrical double layer, you still find that the magnitude of this coupling coefficient is related to that boundary condition for the potential. And the reason for this is that changes in the distribution that are associated with lambda d will change the amount of charge density, and they will change the location of that charge density, but they will do so in a way that does not change the integrated current. Yeah?
Why do you have an n by del?
So, when I write the n, this is basically the gradient in the normal direction, and I mean along the axis. As this is being written, this is a scalar. The gradient of the pressure is, got it? Yeah, so it's just to specify that it's something which in general would be a vector, but I'm only considering the component along the axis of some channel. Okay, so this is where we got to last time. And what this allowed me to do is to now fill out more of the electrokinetic coupling matrix. I had a chi-1,1 from studying electroosmosis. I had a chi-1,2 from studying streaming current. We then added in a chi-2,1. And what I want to talk about next is I want to start talking about the transport of ions, and I want to relate that to the current that we see generated by an electroosmotic flow. And the reason why that is important is that, first of all, a basic understanding of ion transport will allow us to say that the basic answer for this chi-2,2 is the conductivity sigma. And that there's a correction factor to this sigma that comes from the convective surface conductivity. This really means that in the case where we have any sort of net charge at the surface, that net charge of the surface generates an electroosmotic flow. That electroosmotic flow itself carries the ions in the double layer, and therefore there's a current that's generated by the flow associated with electroosmosis. So here we said, well, all things equal, before we started thinking of electrokinetic coupling, you wouldn't think that pressure would cause current. But when we allow there to be a charge at the wall and therefore a distribution of net charge density, now we see that there's a correction here. Even in the absence of surface effects, you might expect that if there's an electric field being applied, that will get current density, and the multiplicative factor that relates those two is conductance. But if the surface is charged, we can have an additional factor here that stems from the motion of fluid. So I want to talk about that convective surface conductivity in a way that is similar to the way we talked about streaming current last time. And I also want to use that as a segue into starting to talk about ion transport, because ion transport is really the thing that drives that sigma up there. Ion transport is the thing that will allow us to take our equilibrium distribution, or our equilibrium discussion of the electrical double layer, and turn it into a dynamic discussion. And it will also allow us to start talking about more applications where we can use electroosmotic flow. Arguably, the only real application I've made so far is I've said that electroosmotic flow makes for a compact pump that can make really high pressure. But another thing that microfluidic devices have been used for, I guess at this point, 2 decades, is for chemical separations. And these chemical separations are typically used to separate out ions that have a different electrophoretic mobilities. So now the relative motion of ions in an electrolyte solution starts becoming important. The flow properties associated with electroosmosis practically make those chemical separations work really well. And in fact, in homework 4, you discussed a relatively complicated geometry that allowed you to take these chemical separations and expand them to long effective lengths without adding any dispersion. So bottom line is I want to talk about convective surface conductivity and segue, and convective surface conductivity is sort of the middle of chapter 9. I want to skip the second parts of chapter 9 and skip chapter 10 and start talking about chapter 11, which is ion transport. So this here is convective surface conductivity. These are the Nernst-Planck equations, which are the basic equations for ion transport. When we sum those over all the ions, we get a net charge density transport equation. And all of these things are linked together and related to equilibrium double layer arguments by the Nernst-Einstein relation, which I've written there. So that's the plan. So you may recall from last time that we said that the total current that's caused by fluid flow is given by the integral over the cross-sectional area of the velocity of the fluid times the net conductivity, or the net charge density of the fluid. In the case of streaming current, we envisioned that this velocity field was induced by a pressure gradient and was parabolic in nature. And then we assumed that we had a charge density that was specified by the equilibrium electrical double layer. So we envisioned a distribution of velocity that might look like this. And then we envisioned a distribution of net charge density that might look like this. Then when we zoom in on the area near the wall, we argue that if the electrical double layers were thin, that this distribution could really be approximated as a line, while this distribution, at least in the Debye-Huckel limit, would be described by an exponential decay. And then the product of this linear green function and this exponential red function gave the distribution of the local ion density, this U times rho E. And in fact, that tells you that if we made a graph of U times rho E, we would get a distribution that looks a little bit like this. There's no current flux far from the wall because there's no charge density. There's no current flux at the wall because there's no velocity. But there's this sweet spot, and the characteristic length of this sweet spot is approximately on the order of lambda d. This is the sweet spot where there's some velocity and there's some rho e, and when I take the product, there's something there. I argued, but did not derive, that evaluating this integral in this case leads us to the conclusion that chi21 is given by minus epsilon phi naught over eta. And you can look forward to a super awesome homework problem where I'll ask you to calculate that. Now, if we consider the case where we have an electroosmotic flow, my rho e is unchanged, but my velocity distribution looks quite different. But regardless, if I zoom in at this area right next to this wall, I am still left with the product of two different functions. A rho sub e and a velocity distribution u. And in the same way, this product u times rho e has a functional form that again goes to 0 in the bulk because there's no rho e, even though the velocity is maximum in the bulk. At the wall, it also goes to 0 because the no-slip condition still applies to the wall. The only difference is that in this case, I have an approximation, or I have a distribution I can approximate as linear, being multiplied by an exponential decay. Here, I have exponential growth being multiplied by exponential decay. So again, the exact mathematics don't work out, but I do get an overlap region where I have finite velocity and finite rho e. I can integrate this as well. You can look forward to doing that on a homework problem also. And when we do that, we find that generates a correction term to this chi22 equation. Remember, chi22 is telling us how much current density do we have normalized by the, how much current do we have normalized by the electric field that's being applied. Now, in terms of terminology, there are a number of different terms that we need to clarify. One is surface conductance. And one is surface conductivity. And we also need to compare convective aspects of these issues rather than conductive aspects. And in this terminology, when I distinguish convective from conductive, I'm distinguishing between two different physical processes. When I distinguish between conductivity and conductance, it's really just a matter of whether I'm trying to describe an interfacial effect as being one that affects the holistic conductance of the system, or whether I'm trying to take an interfacial effect and use it to describe an effective change in the bulk conductivity of the system. So, if I go back to this term chi22 again relates my current density to the magnitude of the electric field in the normal direction. Because this is a current density being related to an electric field, this is basically a bulk volumetric response. And that's why the zeroth order solution to that is a bulk conductivity of the fluid. So this has no geometric information in it. This is just a property of the fluid. If I double the ionic strength, I'm going to double the conductivity. This is now a correction term, and that correction term is being related to an interfacial phenomenon, but it's being used to describe an effective change in this equation that really has bulk parameters. And the difference in language is just the difference between, if I describe conductivity, I'm trying to describe the effect of this surface in terms of equivalent bulk volumetric properties. Or I can take the same information and I can describe it as conductance. And when I do that, then I'm trying to describe it in terms of an equivalent system property. Really, the only difference between these two things is that when I describe the conductance of the system, the conductance is proportional to the cross-sectional area and it's inversely proportional to the length of the channel. The conductivity is not a function of these geometric parameters. So it's really just a matter of whether I'm multiplying something times A and dividing it by L or not. That's the distinction between these two terms. The distinction between convective and conductive surface conductance effect or surface conductivity effects stems from the fact that there are two different ways that an interface changes the conduction through a system like this. What I just described is the convective effect, meaning that in the presence of an electrical double layer, there is electroosmosis, which means that there's a velocity. If I take the integral of that velocity times the net charge density, I get a current. That's this. It is also true that if I solve the Poisson-Boltzmann equation and calculate out the total number of ions near the wall, not the net charge density, but the total number of ions, I find that the total number of ions when I solve the linearized solution does not go up. But when I solve the full solution, that says basically that the exponential growth in the counterions is bigger than the exponential decrease in the coions. And it just means that on average there are more ions near the wall when the interfacial potential is high. Once it's high enough that the linearized solution is not accurate anymore, we find that there's an increase in the total number of ions near the wall. And that means that while this bulk material might have a conductivity that's described using bulk properties, like I have millimolar sodium chloride, so I calculate out what the conductivity of millimolar sodium chloride is, and there I get the answer. If I look right next to the wall, if that potential isn't really, really small, I have more ions and I have more conductivity. And when that happens, not only do I have to add this correction factor for the convection, the motion of charge from fluid, I also have to go back and correct this to make this an effective conductivity including the electrical double layer effects. So we haven't done this yet. But again, everything in this lecture, now that I'm getting through it, everything in this lecture is just a preview of exciting homeworks to come. I'll ask you to solve the nonlinear Poisson-Boltzmann equation for electrical double layers. From that, you can come up with an estimation of how the local conductivity increases as the potential goes up. And in fact, what you'll find is that the potential locally goes up as hyperbolic cosine of the local non-dimensionized potential. So when you start getting up to 25 millivolts, 50 millivolts, 75 millivolts, you'll find that that local conductivity near the wall is high. And at that point, you'll have a conductive component of the effective surface conductivity. This all relates back to our goal, which is to get a description of the electrokinetic coupling matrix that keeps track of all of our key factors. If I start out with no interface, I have this. If I add an interface, I get this. And then if I make that interface even stronger, have a strong enough potential that the equation is nonlinear, then I have to add that. Again, the reason why we put this stuff in the electrokinetic matrix is I want to do all of these calculations in isolation. And then when I come back to you and I say, OK, how does the thermodynamic efficiency of an electrokinetic pump change as I shrink the length scales of the domain? You don't have to do the whole problem anew. All you have to do is say, OK, well, how does this change and how does this change? And I'll take the ratio, and then I get the answer. Or if I ask you to describe electroviscosity, how does electroviscosity work? I basically will ask you to calculate this and this and this and this all separately, take the ratio of a bunch of things, and then you'll be able to tell me how electroviscosity works as the length scales change, as lambda d changes. Comments, questions, criticism? Does anyone have a bone they'd like to pick? Yes. You have a bone to pick?
No, not bone. Just to clarify, you're saying the last correction is for the interface where the potential is large enough that the correction is necessary?
Yeah, so when I say that this goes from sigma to sigma effective, what I'm really saying is that to describe the bulk conductivity, to describe the bulk conductive effect, I have to account for the fact that this sigma in the bulk does not describe the sigma near the wall. And so I basically need to integrate the conductivity across the whole domain. In the bulk, it will be unchanged, but near the wall, it will go up.
So the effective is really describing the change in the wall, but it's entirely.
Correct. And the reason for the symbols that I'm using all comes back to the fact that this equation is a system equation. It's basically describing what is the total volumetric flux through the system, what is the total current through the system as a function of pressure gradient and potential drop. I'm describing it in terms of bulk volumetric properties like viscosity and conductivity, despite the fact that a bunch of stuff is changing across this domain. When I integrate all these effects, I can use that to define these properties. Now, the reason why it makes sense for us to take something that is changing as a function of y and integrate all of it away to get a volume averaged property is that the characteristic length scales, the aspect ratio of most of the devices that we're interested in, typically these things are really long and really, really narrow. So if I have a 50 nanometer deep channel that is 4 millimeters long, the effects I have at the edge effects are relatively easy to ignore, and really all I need to do is keep track of what is the area average effect. That will be the thing that will tell me all the engineering parameters I need to know. If we make the geometry more complicated, then this formulation will cease to become useful, and we'll just have to solve the transport equations in their full form.